Welcome to my talk on PrIC3, Property-Directed Reachability for Markov Decision Processes. IC3, or let's call it here standard IC3, is a symbolic model checking algorithm for verifying or refuting reachability properties of transition systems. IC3 was a breakthrough for hardware verification because it can scale to very large systems, and it has been extended for the verification of software and hybrid systems. We were concerned with the question whether IC3 can also be a breakthrough when it comes to verifying probabilistic systems. So we developed PrIC3, which is an algorithm for verifying or refuting upper bounds on maximal reachability probabilities in Markov decision processes. Our goal is to provide the foundations for a scalable algorithm for the verification of probabilistic systems, and in particular of probabilistic programs. What precisely is a Markov decision process? It combines non-deterministic and probabilistic behavior. So we have a finite set of states, we have an initial state, a set of actions, and a transition probability function that assigns to each state action pair a distribution over successor states. The operational behavior of this example MDP is as follows. At the initial state, there are two enabled actions, A and B. The process first non-deterministically selects such an action and then behaves probabilistically according to the respective successor distribution. If we now fix some set of bad states, for instance S2, then it makes sense to speak about the maximal probability to reach these bad states from the initial state, in this case 0.7. And if we additionally fix a threshold probability lambda, then we obtain a decision problem that asks whether this maximal probability is at most lambda. A Markov chain is an MDP with a single action where no non-deterministic choice is possible, and in this talk I will restrict to Markov chains, even though everything I tell you here also extends to MDPs. What we did in order to develop PrIC3 was first of all developing an understanding of standard IC3 for transition systems on the level of sets and functions rather than formulae and subqueries. If you consider a paper on IC3, then you would see that most things are formulated in terms of formulae and subqueries, which makes sense, but which also made it hard for us to develop PrIC3. This then enabled us to develop a PrIC3 framework conservatively extending standard IC3, or more precisely reverse IC3, because the search direction of our algorithm is reversed. By conservative extension, we mean that if we choose the threshold probability lambda to be 0, then we obtain a qualitative reachability problem, and in this case our algorithm behaves as standard reverse IC3. Furthermore, we provide a prototypical implementation and an empirical evaluation. Here we operate on program level by means of an SMT encoding, and we are able to adapt optimizations well known to IC3 such as repushing obligations, propagation, and we provide first ideas on what is called generalization. Throughout this talk, I will compare to the concepts of standard reverse IC3 so that we see how these concepts generalize in the probabilistic setting. We will see that there are a lot of similarities, but there were also some serious challenges that we had to deal with in the probabilistic setting. For that, we first recall how to prove unreachability in a given transition system. In this example system here, the bad state S4 is unreachable. And in order to prove this, we can synthesize an inductive invariant. It's a set of states that contains all bad states and that is closed under backward reachability. Such a set of states necessarily contains all states that reach the bad states. And if we additionally know that the initial state is not in that set, then we have proven that the bad states are unreachable. Notice that we can equivalently denote such a set of states by means of its indicator function. For Markov chains, we can do something similar. Consider this chain here as an example. S4 and S5 are the bad states. The probability to reach these bad states from the initial state is 0.5. And we want to prove that lambda given by 0.7 is an upper bound. To prove this, we can also synthesize an inductive invariant, which in the probabilistic setting is a map from states to probabilities. Here is an example of such an inductive invariant, and why is it inductive? First of all bad states have probability 1, and for all other states it holds that the value of the invariant at state S is at least this weighted sum over the successor states. An inductive invariant necessarily over-approximates the probability to reach bad for every state, and if we additionally know that the value of the initial state is at most lambda, then we have proven that lambda is an upper bound. We will now have a closer look at the theory underlying IC3 and PrIC3 respectively, and I will start with IC3 and transition systems. Here let us call every set of states, or equivalently its indicator function, a frame. We have a partial order on these frames, which is subset inclusion, and now we define an operator, a frame transformer phi, that takes a frame F and maps F to all bad states plus all predecessors of states in F. This operator defines the states that reach bad in a stepwise fashion by means of a least fixed point iteration, and the set of all states that reach bad is precisely the least fixed point of phi. Importantly, this operator allows us to concisely characterize inductive invariants, because by the principle of Park induction, a frame F is an inductive invariant if phi of F is at most F. In PrIC3, we call every map from states to probabilities a frame, and we also have a partial order on these, which is the pointwise lifted order on probabilities. And now we also define an operator, which is also known as the Bellman operator, that works similar. It takes a frame F, and on state S it returns 1 if S is a bad state, and otherwise it returns this weighted sum over the successors of S that we've already seen on the previous slide. The Bellman operator defines the probabilities to reach bad, which are again given by the least fixed point of phi. And importantly, here it also holds that a frame F is an inductive invariant if phi of F is at most F. With this fixed point view in mind, we now consider how IC3 and PrIC3 work conceptually, and I will again start with IC3 and transition system. What the algorithm does, it computes for an increasing k, beginning with 0, 1, and so on, a sequence of frames, f0 to fk, and these frames must satisfy the following four invariants. The first invariant says that f0 must be the set of bad states. The frames must form a chain with respect to subset inclusion. No frame must contain the initial state, and frame fi plus 1 must cover all predecessors of states in fi. The reason why IC3 maintains these invariants is first of all that then every frame fi over-approximates the set of states that reach bad in at most I steps. And crucially, the ultimate goal of IC3 is to find two consecutive frames that coincide, fi and fi plus 1, because in this case we have found an inductive invariant that does not contain the initial state. If we now consider the PrIC3 invariants, then we will see that they are completely analogous. The difference is now a frame is a map from states to probabilities, and frame safety now says that the value of the initial state must be at most the threshold probability lambda. The reason why PrIC3 maintains these invariants is also analogous to the standard setting, because then every frame fi over-approximates the probability to reach bad in at most I steps for every state. And here it also holds that if we find two consecutive frames, fi and fi plus 1, that coincide, then we have found an inductive invariant for which the value of the initial state is at most lambda, proving that lambda is an upper bound. Now that we know what loop invariance PrIC3 preserves, we will have a look at an example run on the Markov chain we've already seen. So here we want to prove that lambda given by 0.7 is an upper bound, and for simplicity we assume that we have pre-computed that these gray states here do not reach the bad states at all. Our algorithm does not require this, but it simplifies things here. The algorithm starts by initializing f0 in order to satisfy initiality, and then it starts the first iteration initializing frame f1 by means of this trivial over-approximation of the one-step probabilities. The goal of the algorithm is now to re-establish all loop invariants, and we can see that frame safety is violated. It does not hold that the value of the initial state in f1 is at most 0.7. So we want to lower this value to 0.7, but we have to take care of the fact that this does not violate relative inductivity. For that, we now consider the values of the successors in f0 and check whether this weighted sum here exceeds 0.7. This is not the case since both of these values are 0, so we can safely lower the value of the initial state without violating any other loop invariant. Now that we've re-established all loop invariants, we can continue with the next iteration, initialize f2, again by this trivial over-approximation of the two-step probabilities. And once again we see that frame safety is violated, so we want to lower the value of the initial state in f2 to 0.7. For that we now consider the values of the successors in f1 and check whether this weighted sum here exceeds 0.7. This is now the case since both of these values are 1, which means that before we can strengthen f2, we first have to strengthen f1 by lowering the values for s1 and s2. And this is a crucial point where PrIC3 differs from IC3, because what do we have to do? We have to find values for s1 and s2, let's call them x1 and x2, such that this weighted sum here evaluates to at most 0.7. We can see that there are infinitely many choices for these values, and it can indeed be the case that we choose bad values that prohibit us from finding an inductive invariant. So here our algorithm requires a heuristic or an oracle to guess some good values. Suffice it to say for this talk that PrIC3 always terminates regardless of the heuristic and the oracle you choose. However, the runtime of the algorithm highly depends on these ingredients. Dealing with this issue was actually a challenge because we do of course not want to use perfect oracles that require a pre-computation of the exact reachability probabilities. So we developed a heuristic such that it often suffices to only use rough approximations of these probabilities as an oracle. Furthermore, in our paper we provide formal conditions on sound heuristics such that you can develop your own heuristic, plug it into the algorithm, and be sure that what you obtain is still a sound version of PrIC3. For this example run, let's just assume that our heuristic gave us some nice values such as 0.4 and 1, which means that we can finally strengthen f2 and lower the value of the initial state. Now our algorithm continues to behave like that. I will be much quicker now. We have re-established our loop invariants, so we can start a new iteration, initialize f3. Now we have to strengthen f1 and f2 before we can strengthen f3. And in the next iteration, after strengthening the frames, we observe that two frames coincide, f1 and f2, which means that we have found an inductive invariant, proving lambda or 0.7 an upper bound. Notice that I omitted an ingredient that can make the algorithm scale to very large systems. This ingredient is called generalization. And loosely speaking, generalization means to exploit a symbolic encoding of the model to not only lower the value of one state at a time, but of many more. Finally, we consider our empirical evaluation. We compared our prototype to two engines of the probabilistic model checker Storm, the sparse and the decision diagram based engine. We took some standard benchmarks such as BRP and zeroconf and some handcrafted ones such as chain. And in the first column you see the size of the model, then the probability to reach bad, and the different threshold probabilities that we want to verify or refute. The next columns give the numbers for a run of PrIC3 without generalization and with what we call polynomial generalization. Here we see the runtime of the respective benchmark, and this is the size of the considered subsystem in case the algorithm refuted lambda as an upper bound. We can see that without generalization, Storm drastically outperforms PrIC3, but this is not surprising since, first of all, PrIC3 without generalization introduces some overhead, and as demonstrated by recent competitions, Storm is one of the fastest probabilistic model checkers. However, we can also see that for some structurally simple models, our generalization allows PrIC3 to verify models with up to 10 to the power of 12 states. Currently, this only works for rather simple models, so the breakthrough for probabilistic model checking is not there yet, but we believe that further research on generalization will allow PrIC3 to scale to large and more complex models. What I also want to emphasize is that PrIC3 can benefit from the fact that it partially explores the model, because sometimes, as it is the case here for zeroconf, it suffices to consider a very small portion of the model in order to verify or refute an upper bound. Moreover, we see that the closer lambda is to the actual reachability probability, the more time the algorithm needs and the bigger the subsystem it has to inspect. And sometimes it is even the case that PrIC3 times out, whereas for a smaller lambda it is still able to verify or refute it as an upper bound. Advanced PrIC3 challenges include, for instance, refutation. So what does our algorithm do if the threshold probability lambda is smaller than the actual one? And this was also a challenge because for probabilistic systems, a single path from the initial state to some bad state does generally not suffice in order to refute an upper bound. Furthermore, as mentioned in the beginning, we developed an SMT encoding to operate on program level, and we also asked ourselves how to find good oracles, and I would like to invite you to read our paper for further reading on these challenges. To conclude my talk, we've seen PrIC3, a, to the best of our knowledge, first truly quantitative extension of IC3. We've seen that PrIC3 synthesizes probabilistic invariants, and we considered the underlying theory, the loop invariants it preserves, and we saw by example why PrIC3 requires a heuristic. Future work includes finding good oracles and heuristics, generalization, and the question whether we can employ PrIC3 for verifying infinite systems. Thanks a lot for your attention.